开始了。接着我没有时间学习中文，所以大部分用英语。对，突然被邀请进行在线的报告，所以要准备报告，所以没有时间学习中文。但是呢，一步一步提高我的中文的水平。所以如果我的发音不好的话，请指出我的发音错误。没有问题，我没有连，所以后脸皮，所以如果我的发音不好的话，你应该教我准确的发音。Okay, now, so we are doing free bosons, and then do the model expansion, and then this is the primary field, Okay, and then so we use this one as a model. And then they satisfy this commutation ratio. Essentially, so the output free boson is essentially infinite many Heisenberg models. So this is called Heisenberg model. So there, essentially Heisenberg model. And then, so we talk about the stress energy tensor. So, and if you do the plug into this model expansion, you get this one. And this one should have the whatever. The mode is the Arrow mode. So therefore, if you compare these two, we will get the Arrow mode is something like this one. Okay, so that's what we saw last time. Yes. So the Russell model can be written. In the case of free boson, we can write that very simple. So the upper one is not equal to Z. Okay, so therefore, and the Hamiltonian is given by 2 pi L, and then can be written in terms of like this way, like this way. So this is the essentially consistent with the big algebra. So when you study the big algebra, we already encounter L plus L0 bar is the Hamilton. Okay. So first, any question? And then what was that? And then so the Casimir energy. So somebody asked last time, why the partition function? Partition function, right? Taken 函数. Anyway, is trace of q to the L0 minus c over 24. Why do you have this minus c over 24? So this is actually, so I'm going to explain why this is, in the case of the well module, what you get is 8 of q over 1 over 8 of q. So this is a delegate data function, which is q to c. Sorry. Anyway, so q to c over 24 product n is equal to 1 to infinity. Like this way. Like this way. Okay, so that's what we have. And then, so the question is, what is this minus C over 24? This is actually cosmic energy. Okay. So, okay. Cosmic energy, and then, so that's what I'm going to explain. So first of all, what we know is that if you consider the transformation of the source energy tensor, so C is equal to E to the 2 pi L by W. As first, we're going like this way. I think I didn't print it out. Oh, no, sorry. W over L, no, 2 pi W over L. So that's a relation between W and Z. So therefore W is equal to 2 pi log C, like this. Okay, so therefore, and then so we know the stress energy tensor, we have this following transformation. And then minus 2, and then d of t, and then short-term derivative, like this way, short-term derivative, like this way. So I'm not going to write down short-term derivative, I'm not going to write down the definition, but you already knew what it is. So, and if you use this one and plug this one into here and do the calculation, this so that this is the cylindrical component, cylindrical, and this is plane. Oh, sorry, I think I made a mistake. Just a moment. I think what I wrote is not correct. Just a moment. A short-term derivative. I think it's not the overall factor. Whether I write down the... Oh yeah, it's not correct. Sorry. Yeah. So here is C over 12. Yeah, C over 12 involved. That's why. Okay. Fine. So then this will give you P plane. So this is PL. Like this. Fine. So what is the C for free boson? What is C for free boson? Central charge. Huh? Yeah. Free bosons. I mean, here C is equal to 2 times CL, 2 times CR. So therefore C is equal to 1. C is equal to 1. But if you do the computation, you get the 1 over 24 here. So therefore, if you consider the stress energy tensor, the So yeah, here. So if you look at this one, so the stress energy tensor is normal order. So we expect that T of T is equal to V. We expect. So this is expectation. Okay, this is plane. Okay, plane. And in fact, this can be defined as -1/2. So this is the definition. Okay, that's the definition. Limit epsilon goes to 0. Epsilon goes to 0. Del phi v plus epsilon del phi, like this way, and then minus 1 over e squared, plus 1 over e squared. So since we know that this OPE, if you take this OPE of this one, you get the 1 over e squared, and the minus sign, and that AE, yeah, 1 over e squared. So that the I think most likely overall is necessary. Minus epsilon. Overall necessary. So we expect this plane stress energy tensor vacuum excitation value is 0. On the other hand, if you take the vacuum excitation values, okay, values like this way, vacuum excitation value, okay, like this way. So then, so this is 0. So therefore, T minus 1 over 24 to pi over L. So now for cylindrical case, vacuum excitation value is non-zero. Okay, so that's the case. So what does it mean? Okay, so what does it mean for this one? Okay, and we know this one is have a mode expansion of Ln e to the 2 pi and w. Or L, and it's like this. Okay. Fine. Is it so far? Is it okay? Okay, so then, so therefore, this means that the L naught of cylindrical naught. So this one is cylindrical. Okay, cylindrical case. If you look at this one, so what's really happening is that the sorry, I think I need to be careful about the transformation rule for. Sorry, I think I made a mistake. There's a minus sign here. So minus sign. Yeah, it should be minus sign. Okay, minus sign. So therefore, this will give you 1 over 2a0 squared plus sum of n minus n and then n equal to 4. So that's what we are supposed to get. Okay. So since we know that vacuum, so the vacuum n is equal to 0 when n is greater than or equal to none. If it is non-negative, so even a0 analyze 0. Okay, vacuum. So therefore, so everything will analyze vacuum. But so that's why I mean here. Anyway, so here everything L0 or plane analyze vacuum. On the other hand, since we have not trivial vacuum excitation value like this one for cylindrical stress energy tensor, so so therefore so this is equal to so therefore Hamiltonian, if you write down Hamiltonian is 2 pi over L not cylinder plus L not cylinder. So if you write down like this way, like this way, it's totally fine to have this documentation body. So in this case, if you move from one to the other, so if you move to the one to the other, so if you compare between these two, so this is plane. This is plane one. Okay. So then you have h is equal to 2 pi L L0 plane plus L0 bar plane minus 0 plane. So that's what you get. Actually, in this case, 1. Because of this guy. Sorry, not 12. 12. Okay. In general, this become central charge. Central charge becomes central charge like this. Central charge is 重心定. Oh, by the way, thanks for sending me this Chinese, like a Chinese CFD book. I'm going to use that one to learn terminology. Okay, so one book was translated from Japanese book. It's kind of interesting. Somebody translated into Chinese. Anyway, so that's a relation. So what's the difference between so this one? So this one. So here we assume this is plane without shift, but here we need a shift. We need a shift. What's the difference between that statement and this statement? The question is. So this one is in fact obtained by just putting a Hamiltonian is not this Hamiltonian is obtained by the usual way of doing the canonical quantization. Okay. So Hamiltonian density is given by pi times pi times phi minus Lagrangian density, and Hamiltonian is defined by spatial slice times Hamiltonian density. So that's how you define it. Okay. This Hamiltonian, and that is given by exactly this. This is equal to L0 plane, and then L0 plane bar. So that's that exactly this one. Okay. So the Hamiltonian is really infinite line. On the other hand, this Hamiltonian has a length L. This Hamiltonian is the Hamiltonian on the finite side. So if you just consider cylinder, like this one, with radius L. Okay. So therefore, if you put the theory on the finite length, so there is some Casimir 0-point energy we show. That's what you mean. Okay. That's what you mean. So therefore, this is called finite side effect. So this one is called finite side effect. Okay. So these are also finite side effects. So these shift. So in this yeah. So this generating function or like partition function. So we shift by C over 24 because we put the torus. Because you put the theory on finite size torus, and then you just identify the bottom state, whatever state, and the top state, bottom state and top state, and identify together. So sum of all possible parts. That's a trace of the Hebrew space. So this means that when you consider partition function, you consider only like final circumference. Okay, that's why you need this shift because of zero configuration. Okay. Any questions at this moment? Okay. Okay. So now, we consider those are free boson and free fermion. Free fermion. That's what we want to consider. So now the action is given by it's this. So when you say free fermion, if you consider the CFT case, you cannot put the mass because the mass will break the scaling balance. So always, when you say free, usually you can include, if you consider QFT, you can include mass, but for CFT course, you cannot. Okay, and this guy. That's how it works. And then, of course, this is the definition of sidebar. And then, this is the partial slash. So, you know who embedded this notation, right? Who embedded this notation? Feynman used this notation. Anyway, so, and then this game matrix is literally the satisfy this algebra. So this is for conformal algebra. Okay, conformal algebra. Furthermore, we impose a reality condition on the fermion. So psi star is equal to psi. So this is for my reality condition. This is reality. So which means the fermion is real. Okay. And here it's the gamma is the 2x2 matrix, and you can see that in the Euclidean case, this one, this group of algebra, is satisfy this algebra. Like this way. So if you set this one, you can easily see this satisfy this group of algebra. Okay. Okay, so that's the case. And then, so therefore, it's a 2x2 matrix. So therefore, this psi is actually in the capital psi used. Capital psi is two components, psi and psi bar. Because it's 2x2 matrix. So therefore, it's in the case of four dimension, it's a 4x4 matrix, right? This is 4x4 matrix, and you have a 4 component, and 2 wall to another wall, left chiral fermion, right moving chiral fermion, and so on. But in the case of 2D, we have only 2 components for fermion. Okay. Okay. So then we can rewrite. So if you use this one, we can rewrite this action as follows. If you are diligent enough, you can have this benefit. Like this way. Fine. So that's how it works. So if you rewrite, so rewrite. I mean, this is exercise. I mean, if you want, I mean, I didn't include this one in a. I didn't include this one in the homework, but if you want, you can try. Now, so once you have the action, what we need to do is that first you have to solve Euler-Lagrange equation. This time it's super easy to solve. Super easy to find out Euler-Lagrange equation, which is this one. So this means that this is the equation motion. And so which means this one is the anti-homomorphic. This is homomorphic. Sorry, not this. Sorry. It's homomorphic anti-homomorphic. Fine. Yeah. At this moment, it's no problem. Now, so we consider this. What was that? 2-point function. We want to consider 2-point functions. 两点两广函数. I just learned x and y. Okay, so this is what we want to psi I, psi j, and k I j. Okay, so that's case. Okay. So now, so we do the same thing for free bosons. So what we did is that essentially this KAI, Kij is, I mean, if you write down the action like this way, whatever, like this way, J in Lagrange. If you write down Lagrange like this way, this K and A are inverse to each other up to that function. Okay. So essentially K and A are inverse. In our case, so here is Aij. So Aij essentially Aij xy is equal to like this. This is Aij in okay. So what we want, what we have is an essentially delta x minus y, gamma 0, gamma mu, j, delta x, delta mu, k, j, k, jl, xy is equal to delta x minus y, delta y. That's what we have. Okay. Fine. So write down this one in terms of this homomorphic coordinate. So write down, rewrite in terms of homomorphic coordinate for this one is that what we have is that so pi the or 0, 0. Just strange. But it's okay. Okay. So right now, so this is a huge exercise to do, but anyway, so we just accept. We can accept if you're careful now, we can just check. Measures. Is equal to 1 over pi or c minus w and that's so this is equivalent to, so if you write down this one, in terms of, in terms of this one, so this is the case. Here I use the fact that I think, yeah, most likely, sorry, I think I made a mistake of, yeah, most likely I made a mistake. I don't need this one. I don't remember how I did for free balls. Let me check. Free balls on, oh. I haven't, sorry, I haven't printed out. Free balls on, maybe it's okay. Maybe it's okay. Yeah. Anyway, so in this equation, I don't need this one. Sorry, in this equation, I don't need this one. In this equation, I don't need this. Sorry. So this one. I think there's the type of human still. Okay, fine. Then let's move on. And here, so dot function here. So right hand side, you have a dot function here. So, but I use the fact that dot function of x in 2 dimensions can be written down like this way. 1 over pi shell r 1 over c is equal to pi del z bar. That's what I use. How to derive this one? Do you know? Yeah, so you can use the closest term. So if you have the dc square delta x is supposed to be 1, appropriately normalized. Appropriately normalized 1 is then dc square and then 1 over pi del bar 1 over c. Actually, there's a 1 half we will show. Okay. See? And then this one is in fact equal to 0 and 2 pi dc whatever c, and then somehow you need an I. Okay, maybe I here, I here, I here. This is equal to 1. Okay. Is it okay? So the dot function, if you just integrate over the dot function, so I think if you do that, correct, this is a dx squared. I mean, if you do the change, so dx squared, dot function, 2-dimensional dot function, and apply the closest theorem, and then whatever, Stokes theorem, you get the dz integral around the origin, and then this will give you the closest theorem. The same thing for this one. Same thing for this. So right hand side, I use the fact that this dot function can be rewritten in terms of 1 over z, the undefinable derivative x on 1 over z. Okay, that's what I use for right hand side. And then left hand side is just to rewrite everything in terms of Conformal function. Okay. Fine. So this means that this one will give you that the is equal to this. Okay. Fine. Okay, fine. So from here, okay, so by the way, so what are the conformal dimension of psi? What is the scalar dimension of psi? What is the scalar dimension of psi? Yeah, good. So here we have a -2. So we have a scalar dimension 1 for derivative, and we impose the same reality condition. So therefore, you should have 1/2 and 1/2, and then cancel each other. So therefore, if you have a 1/2 plus 1/2, the order here should be 1. The order should be, or the pole should be the 1/2. Okay, fine. So therefore, from here so OPE between these two is given by this one. And fine. So and also the synergy tensor of the pre-kernel can be written as follows: 1/2. This is a straightforward exercise to do by using. This is a stress energy tensor you will get. Which is the okay, so this one can be obtained by up to some factor, over factor down L down R psi, and then what I'm doing? Down psi. So that's what I do. And other only part is just to put everything on the bottom. Okay, so I'm not going to go into the detail of that whole part. Okay. So now we can consider the OPE between stress energy tensor. Okay, so in CFTs, I just want to make a following message. So this is the most important message I think I will give you. So in 2D CFT, given a 2D CFT, most important is information is the central charge. Okay. Okay. So most important information is central charge. So this is the most important. Okay. 最重要的信息。So 是中心点。Okay. Anyway, so to get the central charge, what we need is the TTOP. Okay. What we need is TTOP. Okay. So to get the central charge, so therefore, once you given a two-dimensional conformal field, what first thing you need to do is to compute TTOP. Okay. First thing you need to do. But before that, let's do the simpler one. So this will supposed to have the following whole, C over 2, if it is a whole, non-parallel, C to the fourth plus 2 times t, 0. Like this way. Okay. Like this. So that's what we are going to see from now. So how about this one? How about this one? Let's do the computation. So this is equal to minus 1 half down sine of t and sine t. Okay, and do the OP computation. So there are two ways to do the weak contraction, this one or this one. So, okay. So let's do the first one is number 1 is this one. So then what we get is 1 half sine z and then over z squared. Okay? Because of this one. Because of this. Okay. Is that okay? And plus the second one is like this way. The second one, if you do the OP between this one and this one, you have to bring this one into the left. In that case, this side is the how to say exchanged by this dot side. Because of this exclusion principle, so you have to put once you just flip the order, you have to get the minus sign. Okay. Therefore, you have a minus 1 half down sine t over z. That's what you get. Is it okay? So then here plus sign because of the like this. Fine. So now then do the tail expansion. So we need to find that. So this one is sine 0. This side. Okay. So if you do the tail expansion around 0, you will get like this. So therefore, this side is the primal field with conformal dimension 1/2. And this is exactly what we expect from the dimensional analysis. Is it okay? The same thing we need to do for TTOP. TTOP like this way. And there are lots of way of doing the contraction actually. Okay, there are many ways of doing contraction. So, okay, let's write down everything. Okay. So first way is like this one. The other way is something like the one order. Other way is something like this one. Okay. That's another way to do that. And then the other way is something like this one. Okay, and also and then okay. Okay, all possible contraction I will write. I mean, it's just the first thing I would do explicitly, and this is the last. And this is the last. Do that OP computation. I mean, I have to explain at least once, but the rest you have to do by yourself. Okay, and then this one can contract with this one, and this one can contract with this. So these are construction you have to consider. 6 ways of construction. Okay? Out of 6 of them. And I can give you only one computation. I don't want to do all the computation. Okay? So let's call it this one is 1 and 2 and 3 and 4 and 5 and 6. 6. Okay, number 1 should be equal to what? Okay, so this should be quarter and negative sign and 10. Okay, so to do the contraction between this guy and this guy, so you have to just swap between these two, so you get the negative sign. Okay? And the first contraction will give you something like this. First contraction will be something like this one. The second contraction will give you something like second contraction is 2 derivatives, c and then 0, 1 over c. I mean, I just put that, okay, w like this way, and then you should set w equal to 0. Okay. Do you understand what I mean? Okay. So now for this one, and then w goes to 0. So now for this will give you what? I'm looking at computation. The first derivative is 1 over 4, 1 over 3, and if you do the derivative, you get that 3 minus w square, and if you add this one, you get the 3 minus w square. If I make a mistake, just point me out. So then you get the minus 2, and this is cube. Good. And set the w equal to 0. So therefore this becomes c cube. Therefore this is the 1 over 2, 1 over c to the 4th. Do you agree with that? Do you agree? Seems like what I did is correct. Okay? The second term, you should do the same. But now, here, you don't need to worry about the ordering because you can just contract the OP like the first and OP this one, no need to worry about the ordering. But the only first derivative acts on this one, so. Number 2 will give you something like this one. Yeah, it seems like this is minus 1. Sorry. Oh, like this. Okay. And the rest, and number 3 will give you something like this one. Let's do number 3 honestly. Number 3 is too easy. Okay, number 3 is very easy because number 3 is like this way, so you have to be careful about the ordering. So this will give you. So this is number 3. Number 4 is also very easy. So this will give you something like this one. Okay, so like this way. Am I doing correct thing? Maybe not. Where did I make a mistake? Oh, okay. So there's no math. Okay. Because here derivative acts on 0. So act on 0. So you have to do is the w and z minus w, okay? And take the w goes to 0. So this means that the still z squared. Okay, 1 over z squared. Fine. So this is number 4. Number 5 is something like it's also very straightforward. Minus 1 z squared minus what? Sine of t and down sine t. And number 6 so this one is something like a cube. The cube minus 2 psi z psi z. Okay, so that's what you get. Fine. So that's you need to sum them all up. You need to sum them up. So can you see that? I mean, here you just take a contraction. You have to take the z, the w z minus w. Okay, and w goes to 0. That will give you 1 over z cube times 2. Okay, times 2, and the rest is this minus sign is coming from plus. To take a contraction, you have to swap between these two. Okay. So for permanent, you have to always be careful about how to take OP. So the sign needs to be very, very careful. Okay. And if you sum them up, 1, 2, 3, 4, what you get is that I don't have a space. What you get is the 1/2 t of 0. Oh, sorry, no, t of 0. 1/4 t. Okay, that's what you get. So if you just do that, so this kind of place, you have to do the Taylor expansion around 0. You have to do the Taylor expansion around 0 to make it everything operate at the point 0. Okay, point operate at 0, and then you get this. Fine. Therefore, so central charge of free Fermi is 1/2. Okay. Any question at this moment? So this is the first time, but the last time to show how to do the OPE computation. Fine. So those are the computations. Now, so we'll do the expansion. For ferment, but you have to be careful. Must be careful. Issue of spin structure. So, and the ferment, so if you consider cylinder and go back, you can just put the periodic or anti-periodic, you can impose both of them. And then it depends on the periodic and anti-periodic, the model structure will slightly change. So if you have so on the cylinder, so L like this. Okay, so on the cylinder, if you go back, and then you have to impose periodic cases for Ramon. And then this is the visuals. Okay, so that's the instruction you have to impose. Condensed matter terminology, this is called bounding. Bounding spin structure, and this is called most likely unbounding spin structure. So this is condensed matter literature in the terminology. Why is it called bounding? Because I mean, if you have a circle. And then you just consider the fermion on the circle. It's you can impose both conditions. However, if you fill this circle by disk, it's called bounded. So the circle is bounded by disk. Okay, bounded by disk. No, the disk is bounded by circle. That I think that's the most better. English is correct. Which one is correct English? Disk is bounded by circle. Okay. So then, so here, so if you have a ferment on a disk, I mean, if you rotate 2 pi, okay, if you rotate 2 pi, you have to get the negative side, because I mean, this is a contractible cycle, okay? Contractible cycle to the origin. But the origin on the, for ferment, if you just do the 2 pi rotation, as you know from the quantum mechanics, you should get the negative sign. Okay? So therefore, if you have a disk, if you consider the fermion on a disk, the boundary condition impose this Navier-Stokes. That's why it's called bounding. Okay, so that's the end. So, but if it is not bounding, you can impose either. Fine. So this is our expansion and new. Oh, so this is still typo. So new is 0 for Ramon. And the new is 1/2 for the Navier-Stokes. You know, k has to be half integer for Navier-Stokes. On the other hand, for Ramon, k has to be integer. Any question at this moment? So now, so this is cylindrical current, and you just use this one is 2 pi W divided by L. So this is the transformation you consider to go to the plane current. So then you have to use the usual primary field transformation plane of Z. Cylinder of Z. Okay. So now you have a shift of square root 1 over square root Z. Okay. 1 over square root Z. So this one will give you the following expansion. So that's what we do. So this new is the same as before. Same as before. But now, in the case of cylinder plane, so let's consider cylinder. The plane, this plane. So in the case of so this is a circle. So the special circle is mapped to this circle here. Okay, in a radial quantization. So now, so since you have a 1/2 shift, so which means the Ramond is the deep side e to the minus psi z. So you have a now minus signs for Ramond and for like this. Like this. Okay, so that's the so if you go to the cylinder and then cylindrical current and the plane current, the boundary condition will exactly opposite because of this square root 1 over square root z. Okay. And then, so canonical quantization will induce that the following commutation relation: Bk and Bl is equal to delta k plus L. So this is the commutation relation. Anti-commutation ratio. Okay, anti-commutation. Okay. So this is considered on canonical quantization. I'm not going to derive everything, but because I mean this is not a course for doing all the calculation. Okay. But you are recommended to do the calculation. And then again from here B minus K, K is okay, K negative is the treated creation operator. K is positive is an annihilation. Okay. Any question at this moment? And then we can check the correlation function by using mode expansion. maybe short sector sum of k and q are half integer. Okay, like this way. Fine. So this is only so okay. So if you look at this one, okay. So we know the vacuum is analyzed by okay. B0 is very. You have to be careful about how B0 acts on the vacuum. Actually, this is 0. This is the most important one. So 0 and B0. Because B0 square is equal to, if you do the computation ratio here, is equal to 1, right? Okay. Do you understand what I mean? So if you use the k and l equal to 0, okay? K and l equal to 0. So therefore, so if you act again, so the vacuum is degenerate, like this way. Because if you act fundamental B0, what I'm doing is what? Am I doing something stupid? Sorry, I think I'm doing something really not correct. But it's okay. It should be okay. So, let me. Sorry. But this should be okay. Yeah, I think it should be okay. So, computation relation there will give you this relation. So therefore, vacuum is degenerate. Two state. Once again, B0 square, you go back to the original one after some factor. Okay, so therefore, so it has the degeneracy at the lowest energy in the Ramond Hilbert space. Okay, so it should be okay. So this is vacuum degenerate. Okay. But here now, maybe short sector. Okay. And then here we assume always assume this one. If you consider this one, or you always assume the issue time. Normal ordering. Yeah. Normal ordering. And what's important is that when k equal to q, k plus q is equal to 0. Then we can use this one to get the non-trivial answer. So for instance, if you have a B1, okay, normal ordering doesn't matter, so it is. As long as B1 and whatever B2, or B minus 2. If you have like this way, they anti-commute, right? At least this is equal to B minus 2, B1, and negative sign, right? Is it okay? Because of the anti-computation ratio over there. And the B1 action vacuum is equal to 0. So always, even if whatever ordering, you can use this anti-computation ratio to make it 0 unless k plus q. Let's look at the k plus q case. The simplest example is something like this one. Is the this is negative sign. Is it okay? But B1 analysis, so this is 0. But at least you get the 1. Okay? because of that anti-conditional relation. Okay. So now for k plus q, we make a contribution, and this one become this is exactly what we saw before. Is it okay? So can you do this computation? Is it okay? No need to repeat. No need to repeat, right? So this is k1 half. K is equal to 1 half to infinity. Okay? K is always half integer. Okay. So this is one of us. Okay, can you do this kind of computation? I hope you guys can do that. Is it okay? So should I do the computation? For instance, this means that so this means that z. So let's say k equal to 1 half. This is minus 1, then w is nothing. Plus next is 3 half, then minus 2, and then this is w. Okay? Plus c minus 3w squared plus blah, 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 like this. That's what we have. And this is equal to 1 over c, 1 plus and this is geometric series. But the geometric series is like this. Okay? Do you understand what I mean? Is that okay? So all those. So if you just expand k equal to 1, k equal to 1 half, 3 half, 5 half, you get this kind of series. But if you do the, you get this one. Fine. How about Ramon sector? Ramon sector is there is some issue globally, in fact. For Ramon, okay, so that's what we have. So we have to be careful. So it's the same thing. So before that, maybe I should write down the equation. Maybe k plus k and q are t and bk and bq and zk plus 1 half. And we have to look at this case. So only what's matter is this one. So this one is equal to, this one comes from k is equal to 0 and q is equal to 0. In this case, the what we have is the yeah. So the numerator is something like b0, b0, so which is equal to 1/2 and square root c w. Yeah, this is okay. Fine. And then this is the model expansion. This is exactly, you just set k plus q equal to z. Okay. Now, okay, again, let's look at how it looks like. So this one is something like when k equal to 1, something like z to the minus 3/2 w to the, what was that? 1/2 and 5/2 w to the 3/2 plus some. So this means that this one is equal to z to the minus 1/2 okay, like this way, what we get is that this is 1 plus w over z and w over z squared, like that's what we get. Okay. Okay. So therefore, this one is equal to z to the minus 3/2 w 1 minus w over z. Fine. And if you add them up, what we found is that like this way. Like this way. So therefore, so it's different from the previous one. So the one we obtained by square root the inverse of Kij inverse. From this one you get the psi t psi w is equal to 1 over z minus w. That one, this computation just give you the Levy short. That's the case. On the other hand, for Ramon, so this is Ramon section. So this will be the boundary condition affect two-point function, in fact. But if you take z goes to w goes to z, it behaves like 1 over z minus w. Because I mean, when w goes to z, I mean the upper one just square root part becomes almost 1, and then 2 divided by 2 is equal to 1. So therefore, the essential behavior is something like this. So locally, OP is not affected. So the OP is not affected by boundary condition. However, the correlation function globally is affected by boundary condition. That's one. Fine. Any question at this moment? Okay, sorry. Let's take a break. And unfortunately, today from 4:30, I have to give an online seminar, as I mentioned in my really bad Chinese. So if you have a question, just ask me during the class. So right after the lecture finished 4:10, I have to leave. So please ask question now or during the lecture.
Sometimes express the delta function in another point which there, such as x minus xi over I show z bar 1 over Yeah.
Oh, sorry. I think what I wrote is so this 2, 0 is literally 1,
Yeah,
right?
this is-
Yeah, this is what I meant. So I wrote X something this way.
This is-
Like this way, right? But if you write down like this way, Z minus W, then this one is something like this.
This is Z minus W.
Yeah.
是KDN population X.
Yeah.
Okay, sir.
光线场理论，在光线场理论里，最重要的信息是中心电荷。我的中文其实那么好笑吗？ 请求。好，请求。那我突然接到了，我突然接到了一个在线报告的请求。Is it correct, Chinese? Anyway. Okay, my Chinese not understandable. Anyway. Oh, I see. 太上五度，太上五度，上五度。上五度，太上五度。Okay, then shall we resume? Okay, now we look at the expectation value. So the zero point energy of the cylinder, final size factor firm. By the way, so another way of deriving, so the way we derive for the final size effect is to do the to cylinder W is equal to dW dc minus 2 like this. So that's what we did to get the final size effect. And T of Z is equal to T of Z is given by again from half limit equals to 0 like this one. So for Planck case, so to define the T of Z is for fermions like this. In the previous case, del phi Z plus epsilon del phi Z and minus sign and then plus 1 over E squared, something like that. Yeah, sorry. Yeah, this show. Okay, fine. Okay, so that's what we did. And so the Lipschitz case is just plug this one. Plug this one, plug that one into here, so it's just 0. So it is case T of Z is equal to 0, working before I'm on. Okay, so you have to do this computation. Okay, so here I just plug this 2-point correlation function over there, and that will affect the documentation value. And this is equal to, in fact, is 1 over 6 something. Fine. So therefore, so if you consider this one is the expectation value, the sum of n, like this way. Okay. So when n equals to 0, that do something. L0 sandwiched by vacuum will give you something non-trivial for Ramon sector. That's what it means. Okay. So therefore, so since we know that L0 is the related to Hamiltonian, so this will so the boundary condition affect the 0-point energy or vacuum energy, whatever, or Casimir energy, whatever you call it. Okay. To compute the yes. Okay. So to compute that, what we can do is that the so we do the mode expansion for the plane, the irrational mode, like this way. Like this way, and K and Q like this. Fine, is it the case? Okay, and then here, derivative acts on W minus K minus 2 will give you this time. Okay, and again. And this can be rewrite as follows. Oh, sorry. So this is Z. Sorry, this is Z. Sorry, this is Z. Like this. Therefore, if you compare between this one and this one, so this guy is equal to Ln. Okay. Is it okay? When n is equal to 0. But n equal to 0 case, because of it affects the boundary condition, you have to be careful. Okay? So boundary can affect the L0, how L0 acts on it. So you have to be careful. So therefore, let's write down. L0 case, more careful. Okay, so L0 is something like this one. 1/2 sum over K Z plus okay, so this is the case. Let's look at Navier-Schwarz case. Navier-Schwarz case. So this means that it has the Navier sector is equal to 1/2. Roughly speaking, I mean, so the lowest, how to say, the smallest order. Let's look at the k equal to 1/2. I mean, if you have this kind of expression, just do the expansion just by yourself. So let's put the k equal to 1/2. Then this becomes B minus what was that? 1/2 B 1/2, and this is 1. It's okay. Let's look at the K is equal to minus 1/2. Okay. K equal to minus 1/2. This is 0, so it doesn't affect. Let's look at that. Next is the K equal to 3/2. And this is what was that? 3/2 plus 1/2 2, and B minus 3/2. B 3/2. That's what we get. On the other hand, let's look at the K equal to minus 1/2. And this is equal to minus 1 minus B 3/2 B E minus 3/2. Okay. Is it okay? Okay. And here, so this normal operators that you have to just the creation operator should go to left and then annihilation operator go to right. If you move that one, this becomes plus B minus 3/2 B 3/2. And then this is equivalent to this one, okay? But you get a 3, okay? Therefore, so from the short sector, this will become something like sum of K, BK, B minus K, BK. K is C. So the same thing happened. Okay, so this is 3/2. Okay, so this plus this will equal to 3, and 3 divided by 1/2 is 3/2. Therefore, it's the same. K is 3/2. It's consistent, right? So in the case of 1/2, you only have a distance, okay, and times 1/2, you do 1/2, and same thing. So 5/2. On the other hand, here you get the minus 2. B. What was that? B 5/2. B minus 5/2. And to swap them, you get the minus sign, and then in total you have a 5. Okay. So you have this one. For maybe short sector. Maybe short sector. On the other hand, so Ramon sector, we want to have this property. So the vacuum extension plane one should give you this one. Therefore, 0. Do the same thing. So plug this one into the so like a B0, B0, 1/2. And then do the same thing. So the next is 1, 3/2, B1, B, sorry, minus 1, 1. And then here 1/2. Like this one. So like this way. And then you can pair it. You can pair it into B1. Sorry, B minus 1, B1, and then times what was that? Plus 1/2 plus 3/2 is equal to 2 times 1/2 is 1. Therefore, this is okay. And the next one is the B 5/2. B what was that? Minus minus 2, V2. So here you have minus 3 half V2, V minus 2. If you change the order, if you just combine them, you get the 2, V minus 2, V2. That's what you get. Yeah. Fine, and so on. So therefore, what we get is essentially sum over k is greater than 1 to infinity, k bk minus k bk plus. So if you have this ordering, so it analyzes back. It analyzes back. But what we want is this expression value 1 over 16. So therefore, we need to shift by 1 over 16. This part will give you just some constant. This part is just give you constant b0, 0, b0. 0 is essentially 1/2. Okay, 1/2. But forget about all those details about constant. So when we solve them together, it just gives you some constant and so on. But we forget about this kind of issue by just relying on the vacuum excitation value of stress energy tensor. Right. So therefore, that's the zero mode of the Virasoro algebra written in terms of the generator of the preferment. Okay, so then fine. So therefore, if you look at this transformation, this will give you so T cylinder is the usually give you 2 pi over L square T when Z square minus 24. Okay, so that's what you get from this computation. Okay, so then in the case of the Navier-Strauss, it just gives you this one. So the appropriate factor is factor out 2 pi over L square, and this is minus 1 over 48 for the Navier-Strauss, because C is equal to 1/2 for Fermat. On the other hand, here for Ramon, here you have 1 over 16. You have 1 over 16 minus 1 over 48 is 1 over 24. That's what you get. Okay. Fine. So those are the vacuum excitation value of the cylindrical, or more precisely, this 0-point energy of the vacuum energy of the free Fermi. So it depends on it really depends on the choice of boundary function. Okay. The logical way to derive this kind of the 0-point energy, string theory course and so on, we use following trick actually. Maybe I can use it here. Okay. In the case of the, so essentially to get the 1/24 is essentially that's how we derive usually 1/2 sum over n and runs for 1 to infinity. And this one we usually what we get is like this one. So this n is really coming from this is the ordering. So sum over n minus n and n, and the n is t and half and so on. And for n, when n is negative, so to the normal ordering, you bring the opposite. That will give you constant n here. And if you sum this up, we do the following trick: 1/2 sum of n equal to 1 and infinity n e to the epsilon n, like this way. And then we take the epsilon to be very small. But this one is equal to 1/2 derivative of epsilon, sum of n equal to 1, infinity e to the minus epsilon n. And the minus sign here, okay, minus sign here. And then this will give you something like this, minus 1/2, like this way, and then do the tail expansion. And treat the epsilon is very small, so therefore this one is something like 1 plus minus epsilon, and so on. So and then epsilon plus what was it? And so on. And this will give you something like this one, 1/2 1 over epsilon square minus 12, like this. And 12 plus order of epsilon. That's how. Yeah, sorry, like this one. So yeah, that's how we get. So sorry, if you do this derivative, what would you get? Minus epsilon square. And then here, if you do the minus 1, minus e to the minus epsilon. Okay, so that's how we do it. And then do the tail expansion in terms of epsilon. Epsilon, that will give you this kind of series. And so for regularization, we just get rid of this one. We forget about this one. And that will give you minus 20. That's kind of its goal, whatever. Anyway, this is one way to derive this bosonic case. It's the same for fermionic case too. We can do the same thing, same trick to do the to obtain the this kind of number. Minus 48, 148. Yeah, so in fact, one can do the following thing. So if you consider minus 1/2 sum of r plus 1/2, and r is 0 to infinity, this with the same procedure what I did here will give you minus 48. On the other hand, minus 1/2 sum of r is equal to 1 to infinity r will give you the same computation will give you another 24. Anyway, so that's another way to get this 0-point vacuum energy. Okay, so that's another way to get that. Fine. Vacuum energy for K. Okay. Any question at this moment? If not, I will move on to minimum model. So if I look at the note somebody kindly sent me. So it's the minimum model. Is the G shell, not Z shell. G, I think it's a different G. I think it's a different G. I think just one now. Yeah. I think what was that? Oh yeah. I mean. No, you don't need this one. I don't need. Okay. I don't need it. Okay. Anyway, it's not three now. Anyway, so whichever is okay. So I'll move on to minimum model. Okay. Any question at this moment? Fine. So this one is the first 1984 development BPC. So this is called burst of fully conformal casing. It's a beautiful paper. After you learn 2D CFT, I highly recommend you to read this paper. Okay. What is the minimum model important part of minimum model? So, important part of minimum model, the most important property is this minimum model is only contains. Okay, so the property, so the most important property is the contain finitely many primary fields, primary operators. Finally, they're not infinite. And also, of course, they are closed under OP. What's the most essential property of this minimum model? And then, okay, all conformal weight, conformal dimension, and then and central charge. Rational. It's a rational. That's important. Fine. So that's property. And then so it's labeled two integers, two positive integers labeled. So we call PQ, and when P is next to +1, this is the otherwise non-unitar. That's the one we are going to do. So the really important property is the first two. The first two. really important. This number 3 is actually contingent. No, it's these two. And then here it's important thing is okay. So okay, that's what we're going to do. And that's very remarkably. So this minimal model has the lots of application in physics, in even real world. The simplest example is the Ising model. Applications Ising model. And many other 2D Ising model, and then yeah, there are lots of time critical, blah blah blah, and so on. So lots of interesting models will show up from minimal model. So this is the important property of, that's what we are going to learn. Okay, so right. Okay. So let's study before that about conformal. Conformal family. So we use that. So if you have a primary field, phi is a primary field operator, and there is state operator correspondence. Primary state. And then, so H is defined by Ln is equal to 0 for n greater than like this. And then L0 acts on H is equal to H. But here, L minus 1 and so on are descendant, and so on descendant. What is the corresponding L minus n? Corresponding operator. The corresponding operator is something like this one. I call it phi minus n w is L minus n phi of w 2 pi I. Like this. This is I mean exactly the definition. Oh, sorry. I think I made a mistake. To the power, we need a power. So this is the n minus 1. Yeah, n minus 1. Okay, n minus 1 T of z. Okay, so when you do the expansion T of z, mode expansion or T of z is something like Ln Dn. Like this way, n plus 2, like this way. This literally means that I mean here you just expand around the origin, and whatever, and then T of z can be placed close to the origin. In the case of the primary field is sitting in W here, Okay, and the action of L minus N is just can be achieved by just T of Z is approach to W. Approach to W. Okay. In that case, T of Z should be expanded by something like a in W L N. Some of this one, and if you plug this one into here. And then maybe I should use K instead of M because the K is here. And what we want is just pick out one of the Z minus W part, one of Z minus W. Okay? Because I mean, if you do the contour around the W, well, essentially the cosine integral will pick up around W is the one of the first order pole. So therefore, if you plug, if you only look at this one, what we need to do is that the do I make something stupid? Yeah, it should. So therefore, LK, so Z minus W, N minus plus K plus 1, right? And then, so which should be equal to, so therefore N plus K plus 1 is equal to 0, means K has to be equal to minus N. Therefore, if minus N, this becomes the first order pole. Therefore, cosine integral will pick up first order pole to see the action on phi. Minus 1 action on phi. Therefore, so this state corresponding to this operator. Okay. And the simplest example is that the phi minus 1. T of Z, phi of W. And since phi is the primary field, this has the point, what's that? OBE. Okay, so like this way. Okay, like this way. Okay. And then do the cosine integral around W of Z. What you get is that here what you get is that's what you get from this analysis. It's a very straightforward computation. Fine. So therefore, the first descendant corresponding to it. So this is the Tai Pu Suan. No, sorry, Tai Suan Fu 对应。the Tai Suan Fu 对应 it corresponds to -1 h. Okay, corresponding to. Like, but for higher one, this one or whatever, so it can be like many sort of negative mode can act on the primary field, will be much more complicated. Expressions way more complicated. Okay. Fine, like this. Way more complicated. So now if you consider the Virasoro correlation function, I don't know, this one is I don't know, 广电函数广电函数 ，OK， 关联函数 ，so 第一项关联函数 ，Thank you very much. This is exactly what I want. This is the关联函数 with the descendant operator inside. Okay, 2 pi r. So this one is dz w c minus w. Okay, and the 1 minus n. Okay, t of z minus w x. That's what's going to happen. Okay, and then just plug into here. That's exactly what's going to happen is that the okay. Okay, so suppose x this guy is something like a phi 1 of d1 w1 whatever or w1. Wm like this one. So x is like this. So what's really happening is that here is some phi minus n. W is here, and the other part is something like whatever phi 1, w1, phi 2, w2, and so on. And this one is equivalent to the following. So this phi 1, w1, phi 2, w2, and here is the primary field, phi w, and then t is approaching. T of z is approaching, and then appropriate manner. So the dw, and if you need to do this kind of integral. This is what we want. Appropriately, I missed dz 2 pi I. Okay. This operator approaching. So this is the equivalent situation. Okay. And then here, so ordering just the contour ordering is something like this. This way. They try into this one. But this one can be just go to infinity and come back, and to the opposite way of doing that, like this way, like this way. So this contour can be deformed, go to infinity and come back to here, like this way. Okay. Equivalent to like this way. So therefore, this one can be just write down negative of 2 pi I. So now t, in this case, the t can. So if you just move to the other contour, so the t can act on the other primary operator, like this primary operator. Okay. T can act on this primary operator. So, and what's going to really happening is that the WI or sum of okay, like this way. So the other operator primary, so therefore, if t approach to the primary field, what you get is exactly this part on phi I. So what we are doing is something like this. Okay. This is T phi OP, phi I. T phi. Fine. So therefore, okay, so therefore this can be written as follows. Sum of I n minus 1 hi w minus wi minus 1 over wi minus w n minus 1 wi. This operator acts on I of w. That's okay. So that's the we have. I mean, just do the cos integral for this one. So this one is just the first order. So the wi is just plug into z here. Okay. Not here. Z here. On the other hand, here it's a second order pole. So you take the derivative on this one and plug z into here. That is exactly the first order. Okay. So and I call it this one is equal to chi L minus F. So what's the case we have? Fine. So the other part is very analogous to the case, and then we can just define anyway. So you can ask how many. So there is a so-called Yang-Tam law or a partition function, a partition something like this. Anyway, so this kind of Yang-Tam you can consider. Anyway, so this is lambda 1, lambda 2, lambda 3. So the number of boxes on 3 and so on. So that is corresponding to this ordering of the this way. Like this one. So this is a Yang-Tam law. And then we write down lambda minus lambda acts on H is something like lambda minus lambda 1. I think it's like this one. That's exactly what I wrote. Yeah. Acts on H. Okay, so this kind of state you can consider. And the corresponding state can be also defined. Okay. Corresponding state can be defined as usual. So you can define a corresponding state and then its correlation function. So the corresponding state we write down. We write this corresponding state as doing. So this one we write down like this, minus lambda of w, or more explicitly minus lambda 1 minus lambda 2 minus lambda n and w. Okay, fine. Corresponding operator can be written. So what's important is that So from this analysis, what we learn is that and of course, if you have this kind of correlation function, so the correlation function is the same thing, minus lambda x is essentially you just apply this operator like this. It's the same phi of W and X. You just ask this some differential operator. So L is the Kali L is something like that. Something like this one. Something like this one. Okay. Acts on the so here, so therefore here, this is the correlation function. 光年 sorry. Anyway, correlation function of primary field, correlation function of primary. So once you determine correlation function primary, you just act on differential operator to get the correlation function descendant. Okay. So therefore, once it's determined, you just apply some differential operator. So therefore, this is determined, this will be determined by automatically. Acting on this. So that. Okay. So therefore, so what's important is this guy. So what's important is this guy, and what's important is primary. That's why it's called primary. Okay. So yeah, so that's why it's important. Okay. Any question at this moment? And then, so primary field phi and its descendant, and its descendant of W, and then solve phi minus lambda of W, and these are called it's called conformal family. Conformal family. Okay, so that's the primary field. Okay, any question at this moment? Okay. Oh, primary field. Oh, primary field is translated to G. What was it? 垂迹场. Okay. 垂迹场. Okay. Fine. So conformal family 恭喜家族. Is it no? How do you say conformal family in Chinese? anyway. So that's the terminology. It's just terminology, right? And for instance, in the case of the for instance, if we have primary field and T of T, so this is the phi minus 1 of W, and this is the T of T of the phi of W, and this is in fact 2 H phi of W. Like this. So this OP can be computed by just a straightforward computation by just acting on derivative with respect to W. Okay, so that's the case. Okay, so that's the case. So what's nice is that from this analysis, what's nice is that the minimal model has finite many. I keep mentioning this finite many primary field. Many primary field. Primary field. And OP is they are closed on the OP. Closed on the OP. So if you have this property, correlation function primary field, it can be determined. Exactly. So this is the most important considerance. So if you have finite many primary field, if you know the OP among them, so then you can determine correlation function exactly. So usual quantum field theory. So as you know, so this is the whatever. It's just schematic right now. Like this is phi1, W1, phi n, Wn, E2 minus S, like this way. Of phi, like this way. So usually this one is really difficult to perform. It's almost impossible for interaction theory to determine. So most of the case correlation function cannot be determined exactly. So at the most you can do is that for arbitrary quantum theory, what you can do is perturbation theory and so on to compute this one at the weak coupled regime or some other method, but exact computation is really difficult. Really difficult. But for minimal model, we can do that. Okay. And they are close on the primary means as follows. So they form like this way. Something like a sample P, sample lambda, C to P, 5P. Sorry, I think you did anyway. Okay, minus lambda divided by C. H1 P H1 plus H2 minus HP plus okay, so roughly speaking, it takes the following on the OP. And then since the P is finite many, so this sum is so the important thing is this is finite many. That's the important part. Okay? That's the important part. So that there are only finite many primary fields. This sum is finite sum. It's a finite sum. And the important thing is if you look at lambda is this young tableau. So you can increase number of boxes. This lambda, this is absolute lambda is sum of I is equal to 1 to n number of I. Okay. So this is number of boxes. Number of boxes. But what's important is really the pole. Okay, a pole. But once you increase the number of boxes, the order of pole will decrease because this is negative sign. At some point, it's no longer a pole. It becomes zero at z equals to 0. At z equals 0. So therefore, so what's important is only the finite many operator in conformal family of P. That's the important thing. So once you increase lambda, this is no longer pole. It becomes because negative sign. Okay? Just all the pole decreases. So as you see right here, okay. So this is the primary field, right? This is the 5 minus 1, right? This is somewhat related. It's not this one is 5 minus 1 minus 1. Okay? Minus 1 minus 1. Like this one. Okay? And then the higher order is no longer pole, right? It's no longer pole. So therefore, it's only three operators input under this OPE. Likewise, so if you take the OPE of the primary field, what's important is only finite many operators. Okay. Important because the pole will decrease once you go to the higher order descendant. Using this one, so one can determine correlation function exactly. That's the thing we're considering from now on. Okay, to construct the minimum model, important thing is cost determinant analysis is required. To construct a minimum model, we need to make use of cost determinant. Cost determinant is very super easy. So you just use the some metrics given by the primary field and descendant. You just consider this kind of operator metrics, okay? And then take so this is a matrix and take determinant. So this is a cost determinant. This is cost determinant. H the primary field, and L minus lambda I explained to you. This is the action. And this is a cost determinant. Okay. Let's look at level 1. Level 1. So level 1 is very simple. H, L1, L minus 1, H. So it's just a number. Level 2 is 2 by 2. H, L2, L minus 2, H, H, L minus 1 square, H, H, L1 square, L minus 2, H, H, L minus 1 plus 1 square, L minus 1 square, H. These are matrices. Okay. So level 3, what number, how many number entry? So this is 2 by 2, this is 1 by 1. How about level 3? How many number of columns do you have? 3. Good. So because level 3 you have L minus 2, L minus 1, L minus 1 cube. So those. Okay. And essentially we have PL plus PL. So at the level L. Matrix and level. And you just compute, take a determinant, that is called cost determinant. So why this cost determinant becomes important? It's because if you compute cost determinant, you understand the existence of so-called null vectors, singular vector, and so on. Okay, so if you compute this one, so if you compute determinant, this one is just what was that? H square, H square, right? You just compute this one is H square. If you just number. This one I don't want to compute, but this one is equal to 4h plus c over 2, 6h, 6h, and then 4h, 1 plus 2h, like this way. And take determinant. What you have something like this one. So take determinant, you have so if you take the determinant, it becomes cubic in h. So h minus h11 c. Sorry, I think I should write down like this one. Minus h21 1 2 c h minus h21 c, like this way. So h12 and h21, I think. Okay, it's only a few minutes left. Anyway, so this one is somewhat related to one of our. Anyway, so I'm not going to write down the value. So, but this determinant becomes 0 once you set h is equal to h1 this value. Okay. This means that this matrix is not invariant. Well, when you set h bar, not h bar. This conformal dimension is equal to this one or this one. Okay, it's not invariable means there must be some zero eigen vectors, zero eigenvalue. Okay, so that one is exactly this null vector. Okay, null vector or singular vectors, and that existence will tell you how to construct minimum model. So let's stop here. And I have to leave today. So if you have questions, just let me know next time or via widget.